Wingate, and I was asked to give a talk here. And in a couple of weeks up at Pumping Station 1, we'll be doing a FPGA type class. And so this was kind of a primer on, how does a computer speak with hardware at the edges, and more specifically in this meeting is like you do something in Python, like what's happening kind of down at the hardware level as far as it goes. So in a microcontroller, you have a bunch of pins that will come out, and every pin will have some kind of hardware attached to it typically. And so the example that we have here is what you'd see inside of a Arduino. And what you have are a series of ports. And the way that you can kind of think of these is the same way that you'd think of any other memory address. So you can write bits to some of them, you can read bits from some of them, and depending on which ones they are, the value inside of the register will change based on things in the world. But basically, I guess I shouldn't have unplugged this. Make sure that I plug this in the correct direction. So like I said, microcontrollers these days are very nice, and they come in with a bunch of built-in hardware at the edges that allow you to not have to have external hardware to do a bunch of fun things. On the Arduino, you have basically three main registers that will configure your pins to do different things. You have the data direction register and the port register. And this kind of triangle in the middle here, you can kind of think of this as like an op amp. And I guess I will go into, I guess I can do that now. So you have the data direction register and the port register. And if you write ones or zeros to each of these, you will get different behaviors of the pin. So if we have the data direction register as a 0, you can see over here that we are going to be setting this up as an input. So the little triangle there will sometimes not let anything come in, or will turn on this pull-up resistor over here. Oops. Sorry. And then if you change it to 1 and 0, if you change the data direction register so that we are setting this as an output, then you can flip how the little triangle will either output a signal or not. So let's get into some Python code here. So we just have a little bit of MicroPython, and there's MicroPython on this little ESP32 board here. And so we're going to have an LED that we're going to put on pin 4. So somewhere out here is some register or some bit in all of these registers corresponds to this thing that we're calling pin 4. And that's kind of the nice things that Python and these abstractions give you, is you don't really have to know anything about these registers. You just set up this pin object and it will handle the rest of it for you. So we're creating a pin object. We're saying that we want it to be pin 4. And when we set this pin as an output, we are basically setting the data direction register, saying, I want you to be an output. And then, so let's run this here. So we have our LED, and we can see LED, we want to set the value of the port pin to a 1. So you can do this. And you'll see that the LED now has gone on. Yeah, it's very exciting. Same here, we can turn it off. And because this is Python, we can do fun things and have objects of pins and go through a list. And it's weird with their commenting system. So we can do a little animation if we want, or not. So like I said, we have the registers that we're setting. And so now if we set the data direction register to be an input, we can do a few things. When you're dealing with electronics, you can't just, you often have to, like, you're working with like flows of current rather than just like bottles of it. So if you have your direction register set as an input, you have the data direction as a 0, and you also have the port at a 0. This is called a high Z state. And so no current will be able to enter anywhere. So typically if you have something like this, you'll have to have some external components that will allow like a flow to happen. And I'll get a little bit into that a little bit later. But typically the way that we're going to want to use this, if we have a button or something, is to have a pull-up. So what's going to end up happening is this pull-up is going to just lightly pull the voltage up to our logic voltage, which in this case is 3.3 volts. And because we've kind of lightly pulled it up, we can use other things to pull it down. So we'll comment this out. We are going to set up a pin. So now we're going to take pin 14, and I just so happen to have it connected to these alligator clips. So this one is ground, and this one is connected directly to the pin. And now that I'm here and actually doing this, I see how like kind of Frankenstein-y alligator clips are, but I wanted something that you guys can see. So we'll stop this, we will save it and deploy. And you can see here that I just am reading the switch and waiting a little bit and just printing it out. And we're just doing that over and over. So like I said, we set up the pin, we set up the registers to set it up as an input. And then we are also setting the port register to say, hey, will you turn on this pull-up resistor, which is why we see a 1 here. Now, as you put this together, you will see that it goes to a 0 because we are lightly pulling it up with the pull-up resistor. And when we short this to ground, then it will go down, but the pull-up is there so that when we let go of the switch, then it will just kind of automatically go up. And so the pin register is the one that we're actually reading from there. And again, this is just like, could be thought of as any other type of memory address. We're just going to shift the bits out of this register and pin whatever that relates to whatever we're calling pin 14 is some bit in that register as we're pulling it out and just reading it. So that's the like basics for just regular inputs and outputs. And then as things get a little bit more fancy, we actually have some dedicated hardware inside of there that will kind of take care of a lot of that for us. So we will now set up another pin here. This one just so happens to be 35 as an analog to digital converter inside of here. So we're saying we're setting up a pin and attaching it to this analog to digital converter. And we're going to read this, and we are going to also sleep. So let's. So the way that I have this set up right now, there is a capacitor on here and a few resistors that just kind of pull it the way that we want to. And I'll kind of show you like what's happening on the inside. So as I push this button here, you'll see that like the voltage drops down, and depending on what capacitance you have and what resistors you have will say how fast this signal will drop down. So when you think of having a knob on something, what actually happens is they have a capacitor that drains much, much, much faster than this one. And when you go to read it, you have another piece of hardware inside of there called a comparator. And so it's going to say, okay, I have one voltage over here and I have another voltage over there. If this one's greater than the voltage, I'm just going to output a logic high. As soon as it crosses that threshold, it's going to put logic low in there. So what's going to end up happening is it's going to start off and it's going to start draining. And then as soon as it matches, as soon as it crosses some threshold, it knows the time constant and it's able to put out some value. In this case, it's a 12-bit number, 495, 4095 to 0 in this case. Excuse me. You guys don't know how lucky we have it now. When I first started doing microcontrollers and everything, that's how it was. It's like, oh, you want to read a potentiometer? Go grab yourself a capacitor and some resistors, calculate your own time constants, and do all of this manually. Some other specialized hardware inside of here. Pulse width modulation. So especially in Python, you don't really, there are a lot of like low level things that you just sort of don't really want to have to deal with directly. Reading analog voltages is kind of like one of those. You don't really like want in your event loop that we're going to have to keep checking in on this pin all the time. We can have some external hardware just kind of take care of a lot of that for us under the hood. So let's comment this out. So I have set up this PWM0 object. And again, this is the PWM hardware kind of sits behind, or more to the point, off to the side of everything that you kind of see here, and will write, in this case, you can kind of imagine this writing to this port register to flip the pins how you want. So in our case here, they give us some nice tools. We will create the object, give it a pin object, and we're going to set the frequency to 5,000 hertz. So 5,000 times a second, it's going to turn on and off. And we can call the duty method on it. And this is it wants a 10-bit number. So anything from 0 to 1023. And so we have the LED at half brightness or full brightness. And we can do little animation. So again, this is how like your standard Arduino does it. And it's very nice that tools like MicroPython and everything allow us to abstract away. The next slide here, this is actually what you'll probably find in most of your M4 and M0 type microcontrollers that you have nowadays. So again, we can start with the outputs. There's a little bit more registers to do everything. And the transistors that are actually inside of these aren't really powerful enough to kind of do anything in the real world. So they give us some MOSFETs that we actually drive. And now things can get a little bit more complicated with like the data directions. So this whole thing right here is kind of the data direction and port pins. And the kind of granularity you can have on the way that you set these up is a lot more refined in this area. So when you want to write high out to something, you'll turn on one set of MOSFETs. Like I was saying, with setting it up in the high Z state, how nothing can get in, sometimes you actually want, like if you had something connected and you had this capacitor on here, and when kind of nothing is happening, you want this capacitor to like drain out. You actually like have to give the electrons somewhere to go. So you can open up a drain on it. It turns on a N-type MOSFET. So you have P-type MOSFETs, which will give you a high output, and you have N-type, where you'd have some high voltage level, and when you turn it on, effectively, you're allowing things to go down to ground. It's kind of opposite. You also get a pull up and pull downs, a little bit more refined on the hardware that comes in and ends up at your pin register. You have a Schmidt trigger, which in this case, you can kind of think of it like you will have some voltage. With digital logic, a lot of times you'll have these little devices that will kind of take variable inputs, and depending on its state, it will either just like throw something all the way high or throw something all the way low. With digital circuits and with these pull-ups and pull-downs and everything, you really kind of don't want to be near the 1.8 volt threshold that a lot of transistors have. You kind of want to just like slam right past them, or you don't want to sit right at the edge, especially with your high frequency stuff, because you don't want it turning on and off. So Schmidt triggers and some of these other things kind of act like a hysteresis device. So like you can think when you have the air conditioning on, you want to have the air conditioning come on, and it'll go on until it hits 70 degrees. It starts getting warmer, but it won't go on again until it hits like 72 degrees. So yeah, I think that was about it. Questions? Well, I mean, what do you want to do? Yeah, well, blinking LEDs, you know, like this is a Wi-Fi connected device. So if you want to, you know, have some web page or something and turn on and off LEDs, LEDs are the easy thing, but you can think of LEDs also, you know, we're turning on a motor, or we're turning on anything that you can think of in your mind that you put a light switch on. You can effectively do the same thing here. If you want to, on the input side, we have buttons, but we also have, you know, temperature sensors or tilt sensors, or, you know, an O2 sensor. Oh, CO2 sensor. Yeah, all kinds of them. Touch sensors. This thing? This is just a ESP32 controller, and it's currently running MicroPython.
Is this like something you pick up at Micro Center or?
Yeah, they probably have them. They're all over, kind of everywhere. Amazon, and your Adafruits and your smartphones and all those will have a plethora of sensors and input, outputs, motor controllers, anything you want. Cool. Thank you very much.